Okay, so I decided to talk about something relatively light or something that may be familiar. I don't know. Is everybody aware of this new buzzword, Planckian dissipation? When you're really in touch, then you've kind of figured out that when you want to smuggle your paper in a glossy magazine, it's a good idea to discern whether you are dealing with Planckian dissipation. It's up to a famous person doing twisted graphene that had actually a science paper with Planckian dissipation, just in the title perhaps. So I thought it was kind of fun to give you an update, because the bottom line is that I am the root of this work. It started really with me. And it goes back to, you can see it, it's 2004, quite a long while ago. And I had the marching order to produce a popular piece for Nature, this commentary piece called News and Views. And I had to do something that was quite complicated. And I wanted to do some dimensional analysis, right? Because always kind of light stuff, relatively speaking. But it turns out that News and Views does not allow in equations in the text. I had a text with equations, and that was got in the hands of a News and Views Nature editor. She was a biologist, a lady. And she turned out to be extremely competent. And the bottom line is that she got the idea to make here a figure containing equations, and it was legal. Now, when you look at this figure, it's about Ohm's law, and I don't want to explain what it is. It's almost so essential right now. But here appeared that word Planckian dissipation for the first time. So what is it? It's about a time that's set by h bar divided by kBt. H bar is h bar, Planck's constant, and T is temperature. As a number associated with dissipation, right? Converting useful work into heat, things that are as of relevance to climate, etc. Now, this has basically sort of a sleeping existence until recently it started to pick up, right? So this is sort of the classic so-called Sleeping Beauty paper in the citation index. You see that it started out here with perhaps 1 or 2 citations. Last year it was 30, but then you can look up all sorts of papers, and there's lots of science and nature stuff out there, right? So it are the more serious papers doing it, where you don't use the word Planckian dissipation. You may be a bit backwards, so strongly recommend to use it when you want to lend your papers into prestigious journals. So what is the story? Why did I invent that word? Oops, just over here. It's all about the famous linear resistivity in the cuprates, right? Everybody knows about it. That it really started out very early with linear resistivity, and it's a landmark, big mystery thing in the cuprates. Extremely simple, but nobody really explained it. It has been hanging above the community for many, many, many years now. Now, what I knew was the origin of this linearity. And this went in my life back to a paper that appeared a year earlier in Nature, and I was actually, I think, the second author or something. It was the only baby that Dick van der Malen and me produced together, at least until very recently. And you might know this paper is basically about explaining that in the cuprate optical conductivity, you have this very long tail in the dope systems, in the optimally doped systems. There's a perfect power law, actually. That was the main deal of the paper. But Dirk produced also this beautiful scaling collapse, which is about the low frequency end. And the scaling collapse is just proving that what you have is a pretty perfect root peak here with a fixed root weight that's not varying as a function of temperature, and instead the width of the root peak is varying according to a time that is h bar divided by kBt. In a moment, I think I'm gonna get rid of this. Yeah. So this is much more recent data. It's by 8.Zaanen in Amsterdam. We was doing a real very high precision study of this low energy end of the optical conductivity. And what you basically have is the black line is optical conductivity, and you can take this apart in a root piece that is the blue line, and another piece which is a long tail thing. Now, why do we know it's a perfect truth? You go to very low frequency and you see how it asymptotes to zero and you find it's perfectly quadratic, right? It really means that should be a truth peak. And then you look at the width of this truth peak and the weight, and you find out that the weight is temperature independent and the, oops, what the heck is going on here? There's something up here. And the truth width is varying like kBt divided by h bar, rather precisely. Now, the real meaning of this is often misunderstood by people who get overtrained in solid state physics. They think that it's about simple-minded particles that are scattering around, and their scattering rate against this order sets the width of the truth peak. It's not true. It's actually extremely generic. You get a truth response when you start out with a system in a Galilean continuum where momentum is conserved, and when you're dealing with a finite density system, it means that you always have a perfect conductor. And a perfect conductor means in optical spectrum, you find just a delta function at zero frequency. And then you break translation advance a tiny bit, and you get momentum relaxation. Total momentum is not forever conserved. And that produces the truth width. So a truth peak basically means like you are very close to a situation where your electron system thinks that it lives in a perfect Galilean continuum. Right? And the electron system can be anything. It can be, you know, you will see in a matter of minutes, that it may be actually like a hydrodynamical system. It might flow like water, which is highly collective. Right, so the bottom line is that the linearity of the resistivity is rooted in the fact that the momentum relaxation rate goes like kBt divided by h bar, or the momentum relaxation time is set by h bar divided by kBt. And this I call Planckian dissipation. Before I say anything else about it, I first have to do an apology because I put a horrible misunderstanding on the map that should be corrected at any occasion, including this one. You read my news and views text and you read, but to convert energy into time requires quantum physics. The uncertainty principle relates energy and time through Planck's constant h. Putting all these pieces together, blah, blah. So the basic statement is Planckian time is abound because of Heisenberg's uncertainty relation. Very simple. Del E del T is equal or larger than h bar. Del E is like temperature kBt, so you have a time scale or the bound to a time scale that's h bar divided by kBt. Actually, this is complete nonsense, and I apologize for it. And I realized it when I wrote a piece, but I had to keep it simple. Right? And everybody knows simple quantum mechanics. The trouble is that Planckian dissipation has nothing to do with quantum mechanics, which is the quantum physics of one thing. It has everything to do with quantum field theory. And quantum field theory has different laws than quantum mechanics, and we'll reveal in a couple of slides how to think about it very generally. There's a very general way of understanding the Planckian dissipation, the claim that it's a lower bound for, in essence, an entropy production time. We cannot do it faster. So this was basically ignored. Some old times may remember that in some remote past, I've likely talked about Planckian dissipation at the SUPERSTRIPES meeting. Been in love with it all along. But it was basically picked up by Andy McKenzie, and they produced this paper in 2013, which is plot here. All you need to know is that when you are on the straight line, alpha is 1, you have Planckian dissipation. It's basically a prefactor out there. And you find all kinds of interesting systems out here. Right at Morales, you find it in ITC superconductors, heavy fermions at the critical point may also show an resistivity, and they also seem to do a Planckian job, blah, blah. Twisted graphene is supposed to do a Planckian job. So it's quite ubiquitous in these non-thermal liquid special states, special metallic states. However, here was also some confusion introduced, because they included here at the high thermal velocity end of things, conventional metals like copper and gold. And actually, yes, these have a momentum relaxation time h bar divided by kBt, but this was understood already in the 1930s. I guess Piles was the first to understand it. And this is understood completely in a semi-classical old-fashioned language. And semi-classical, of course, means it's like kinetic gas theory, so you have a very dilute system of charged carriers. They really don't talk to each other much. Once every 45 minutes, they collide against each other. And they may then learn about that the momentum is not quite conserved, and actually this linear resistivity comes from scattering of electrons against high temperature phonons, and perfectly well understood. It basically amounts to a disclaimer, because you have to be a bit careful. By these old-fashioned semi-classical means, you can get Planckian dissipation, and it's basically a pure conspiracy in dimensional analysis. The reason of this Planckian number is completely different when you're dealing with old-fashioned semi-classical stuffs. Also, recently stories appeared about high temperature phonon heat transport by Daniel Kapitulnik. Turns out to be semi-classics, and it's explained by John Hartnell and his fancy girl student. There's also a story about the viscosity minimum classical fluids by Trashchenko et al. It's kind of interesting story, but again, it's strictly classical stuff. It's not quite quite kinetic theory, but it has the same morale. So just to give you a short impression how you can get at the Planckian number in old-fashioned classical stuffs. So we consider dilute gas. It can be any gas. It is actually like a classical gas in semi-classics. And you assume that you have momentum relaxation due to scattering of static disorder. So you say 1/tau is your rate, Ni is the density of your impurities, Vf is the Fermi velocity, the semi-classic, so the electrons move way faster than classical particles would do, and it's temperature independent. That is kind of important to get this right. A is the scattering cross-section. And now you say, okay, I'm dealing with acoustic phonons way above the Debye temperature. And then the action towards electrons is basically like that they cause kind of a static disorder. Right? So you can take snapshots of the lattice because of the thermal motions, just look disorderly, and the electrons scatter against it, and they behave like a dilute classical gas. So the density of your disorder goes like one of the volume of the unit cell is typically the Bohr radius. Your Fermi velocity is set by h bar divided by electron mass, and again the Bohr radius. And A, the scattering cross-section, is then associated with the typical disorder due to the jittering, thermal jittering of your lattice. The typical disorder sinusoid, that is the mean displacement squared expectation value, is set by equipartitioning. So K is a force constant. Assume that to be Coulombic is E squared divided by Bohr radius cubed. Of course, you know the Bohr radius, you plug it in, and surprise, 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 you find now for this momentum relaxation rate, kBt divided by h bar. So the fact that h bar enters here is just associated with the fact that the Bohr radius and the Fermi velocity know about h bar. That is just a UV cutoff. Atoms form solids, right, at the scale of the Bohr radius, and then you have a typical Fermi velocity like this. Right, so there's nothing to do with fanciful stuff. The real Planckian dissipation proper, as I meant it in 2004, is a completely different story, and it has instead to do much more with quantum computers. I think that the coming of the quantum computer is in this regard rather helpful to get across this message. Right, so you may have learned about that recently. The supremacy of the quantum computer was demonstrated, basically saying you make a quantum computer out of 55 qubits and can do certain computations that cannot be done by any classical computer because of the quantum complexity. What is the big deal out there? It's very simple. You know, we all realized that perhaps already in high school, but we didn't quite realize it because of psychological reasons. It's so ugly that you would like to stay away from it. It's about the enormous size of the Hilbert space of quantum anibolic problems. So when you have 2 quantum bits, you make 4 configurations out of them, and the total Hilbert space of 2 bits is 4, and you know them. You take 3 bits, and you have a total of 8 configurations. Now, the physical world is just made out of things that are, morally speaking, like quantum bits, quarks, electrons, etc. Right? Now, the trouble is that you have 10 to the power 23 of these quantum bits per gram of normal matter. So you're dealing now with a Hilbert space dimension that's as large as 2 to the power 10 to the power 23. There are 2 to the power 88 baryons in the universe. And when the universe would be classical, you would have to solve a system of 2 to the power 88 coupled equation of motions, and you would know everything. And now you see that 1 gram of matter has a complexity, and I start to talk information language, mathematical complexity, see it is exponentially larger than the whole classical universe would be. Right? And it's just an extremely bad problem for us, because we are supposed to get completely lost. So when you have only 55 bits, you cannot compute anything precisely any longer using classical computers. Now you have 10 to the power 23 of these things. How can it be, for God's sake, that we can write textbooks about physics, doesn't matter whether it's high energy physics, condensed matter physics, whatsoever form of physics, that are right, that work? We can turn to our hobby, which is the nature of matter. And it turns out that we have been doing real cherry picking, because forms of matter that are dominating our textbooks are often an supremely special kind. Yes, it's ubiquitous, you find them often, but it's not said that this is the only form of matter. In the language of quantum information, you call these things short-range entangled product states. And the bottom line is that your many-body wave function, instead of being a green superposition of all possible states in a very big Hilbert space, is dominated by a particular state. And a particular state is basically like a classical bit string in a computer. And these are called tensor product states, very simple. Take a table, right? That's state of matter. How do you make it? You make a periodic array of real space wave packets, and then you plug in one atom in every wave packet, and that means that your wave function, of course you can write a wave function, is its product state. Then you're supposed to dress this up with local quantum fluctuations, so you mix a couple of these states out of the big Hilbert space, actually a logarithmically small part of it, and you can do that by perturbation theory, that is polynomial complexity in information language. And then you look at it and you zoom out and you go to the macroscopic dimension, you find out that because the wave function state is dominated by this classical state, that the table as a whole is described by the classical physics. It's described by the classical theory of elasticity. This little recipe is basically a secret of what we have been doing all along, both in high energy and in condensed matter physics. In high energy, you call it semi-classics. In condensed matter physics, it's, all states of matter that we know of are written like this, including, say, the BCS superconductor is very manifestly pair. This thing is, of course, representation independent, so you just go in momentum space. Even the Fermi liquid is in this sense a classical state of matter, because it's dominated by this product, sort of beefed up by the Pauli principle, but it doesn't really interfere with the classical nature of the state, right? And this is a Fermi gas, and you then unleash some diagram to get the Fermi liquid, right, which is again the short-range entangled version of it. Is there a law in nature saying that all ground states of matter have to be of this classical kind? Actually, the answer is no way. We have now lots of examples where it's not true, and that are all states of matter that are so-called topologically ordered. You can basically look up a paper by Xiaogang Wen from 1992, where I explained that topological order really means that you have a state of matter that is many-body entangled, but in an extremely sparse way. And it only manifests itself in these weird global properties of the state. The hardship is topological matter is incompressible, right? You can't say it is isolated from all excitations by an energy gap, that makes life kind of easy. How to think about compressible matter, matter that does not have these gaps out there. And the bottom line is that until very recently, we nearly knew nothing about it. The only thing that we knew was what field theorists call conformal field theory, what we call Steffian quantum critical states, and I will allude to it in a second. There you can say quite a number of things without really being able to solve it. And there was actually a lot of enlightenment recently because there's now new machines that can address the physics of densely entangled compressed matter. I like to call it quantum supreme matter, referring to the quantum supremacy of John Pascal. And these machines are, to a little degree, the such as Yankee type models. They are tiny, tiny little piece. And there's this big so-called ADS-CFT machinery coming from the string theories that I've been working very hard on for the last 10 years or something. So why do we know that quantum supreme matter should exist? There's actually a theorem. It's deeply related to, in order to see it easily, you better learn about path integrals, right? So you write your quantum problem as a problem in space-time, which you're doing to a degree, things that look more like statistical physics. That is, when you have a quantum problem that maps onto an effective statistical physics partition sum, the quantum information people call it stochastic, then you can unleash all the powers of stochastic mathematics to it. It's basically set physics, and we know a lot of things about these states of matter because we understand quite well these things that you can describe by statistical physics. However, generically, this doesn't fly for the reason that generically a quantum problem will not map onto a stochastic statistical physics problem. It's called non-stochastic quantum physics in the quantum information community. The bottom line is that you find out that there are so-called negative probabilities. These are the signs. And in particular, when you're dealing with a system of strongly interacting fermions at a finite density, you will have these signs, and they make the problem mathematically very ill-behaved. There's actually a claim that a theorem exists that is non-stochastic quantum physics is so-called non-polynomial hard. And that's just another way of saying that the quantum problem should be quantum supreme. It's done by Troyer and Wiese, right? And the bottom line is that these non-stochastic fermion type problems are very high on the benchmarking list for the future quantum computer. They'll be the first thing that will be tested, everybody expects. So, do we need a quantum computer? Not quite, because nature is nature. And strongly interacting fermions at a finite density are our bread and butter. We do it all the time because it's only correlated electron systems. But of course, the guinea pig is high TC. Now, I'm myself of the very strong opinion that high TC is a triumph when it's about experiment. We have learned more new physics from high TC than it seems anything else in all of physics, with the exception perhaps of the dark sector of astronomy. And at the same time, an intellectual crisis. When I was a young kid, big meetings on ITC were dominated by plenary speakers that were theorists. Nowadays, you don't find any theoretical plenary speaker for the simple reason that we have been failing badly as theorists. And the reason is we didn't have any mathematical machines. Theorists need mathematical machines to be successful, and our mathematical machines, basically dating back to the 1950s, did not work. Anybody who's thinking differently is just staring away from the real shit. This has been a catastrophe for theorists. We need new equations. And one of these new equations alludes to the linear resistivity. That's perhaps the landmark of the failure of theorists. Okay, this kind of new language really started in the 90s. With SUPERSTRIPES writing this beautiful book about quantum phase transitions, and he was basically resting on the discovery of Sudip Chakravarti. I mean, it should really be blamed on Sudip because he wrote these things down in the Chakravarti Nelson Helpman paper in the late 1980s, and Subir took it up. That was a big deal. You go to this sector where you can get away doing stat phys, no fermion science. These are typically bosonic problems. What you want to do is you have an ordered phase and a disordered phase at zero temperature. And there may be a quantum phase transition that's continuous, connecting the two phases. And now you can rely on stat phys. You go to so-called imaginary time. And you can just write down your stat phys action. Right? So this 5-4 theory, which is Wilson-Fisher critical theory that's coming. And from Wilson-Fisher, you learn that when your dimensionality is less than your upper critical dimension, typically 4, it's now space-time dimensions. So when it's larger than that, the self-interaction is disappearing and you land with non-interacting critical state, and it carries simple particle-like excitations. However, when the self-interaction is finite at the fixed point, which is typically true below the upper critical dimension, in fact, hell breaks loose. It's not generally realized, but the strongly interacting critical state defined in this way is classically NP-hard. You can approximate it very well, but you cannot solve it. The bottom line is that you're much helped by the fact that scale invariance is generated at the critical point. In other words, all your propagators or all your correlation functions whatsoever are algebraic, which means that in the quantum realms in real time, they turn into the so-called branch cuts. And you pick up the anomalous dimensions. Right? And when you think about this, these things really represent what we like to call unparticled physics. There's no such thing as a quasi-particle you can discern. It's one big entangled quantum mass in the quantum interpretation. All excitations are of this kind. There are no such things as particles. Everything is entangled with everything. Now, I learned from Subir what happens when you go to a finite temperature. Right? So you go to the critical state, it's strongly interacting. And now, if this strange rule from thermal field theory that when you have this imaginary time and you want to address temperature, you address temperature by saying, oh, the imaginary time axis forms a circle, and the radius of that circle is set by h bar divided by kBt. So now you want to address what it all means for your observables of your quantum critical point. You go to a finite temperature. What's happening at zero temperature? You have this strongly interacting critical state. It's universal. It satisfies hyperscaling, meaning don't worry about perturbative corrections. And now you switch on temperature and you find out that you're not quite scale invariant any longer because your time axis is finite. That's the scale. You have to do finite size analysis. You can write down all kinds of scaling functions for that. The big deal is that you have to Wick rotate from imaginary time to real time, and it's a very badly defined operation. But one thing is simple: when the relationship between imaginary time and real time is local, a long imaginary time is like a long real time that we can see. So you do an experiment at a time long compared to your imaginary time axis length. And what you find is, by Wick rotation, by rotating imaginary to real time, that at these long times, you find out that your system is doing relaxational dynamics. It's producing entropy. When you're sitting at time short compared to that, you get to see your beautiful branch cuts, blah, blah. Now, the relationship between imaginary time and real time is local. In other words, that time scale in imaginary time is h bar divided by kBt. That has to translate to a single time scale that's governing relaxational dynamics, and that will be there for the Planckian time. Right? So in order to see your Planckian time as relaxation time, what you need is A, dense entanglement, and B, scale invariance. Now we now know that it's much more general, and we know it because of this magical ADS-CFT machinery that basically mapping your densely entangled, very strongly interacting quantum problem onto an equivalent classical gravitational problem in one higher dimension, and then you study here all kind of weird black holes, and these black holes turn into the way that the low energy physics works in your quantum world. I don't want to spend any words on it. You don't have to understand any of it, other than that I will refer to some results only coming out of this fantastic machinery. So, how to understand this Planckian dissipation? Let's go a bit more radical, and let's try to think about how extreme non-equilibrium physics works in these densely entangled worlds. Has everybody already picked up that other marvel coming from quantum information called eigenstate thermalization hypothesis? Perhaps not everybody. Let me explain it very quickly. It's in a way very simple again, something that everybody could have realized in high school. The classic way of setting it up is to say we prepare at time t is 0 a state, a pure state, that's a coherent position of energy eigenstates. They're highly excited, and highly excited states are always quantum supreme. They're always delocalized in a very, very, very big Hilbert space. No way to avoid it. Then we let the system loose, right? So you get the usual unitary time evolution. But now the trouble is that we live on the dark side of the collapse of the wave function. We cannot possibly follow the whole wave function. All we can do is measure expectation values of local operators. And the meaning of local is local in extremely big Hilbert space, something like what's the density of a particle at this or that site, something of that kind. Right? That harvests an amount of information that's logarithmically small compared to the exponentially large Hilbert space. And now the eigenstate thermalization hypothesis is saying when you wait long enough, the answer you get for this expectation value cannot be discriminated from the answer you would get for the expectation value of that operator in a thermal state. It's called a hypothesis because in order to prove it, you need to have full control in your extremely big Hilbert space, and you don't have it. But it seems to be universally true. Now, a way to understand it is, it's a very generic, it's a very intuitive thing, right? So I like to informally formulate the ETH principle as any local observer gets overwhelmed by the enormous amount of quantum info in the physical world to such an extent that he or she does not know better than that everything becomes a thermal state at long time. Right? So you have this enormous amount of information. Here you can only harvest a tiny little piece of it. And basically the same kind of experience as you have when you, as a physicist, try to charm somebody from the other gender when you're heterosexual in a pub. Right? So I know it from my childhood. I learned something very cool about black holes whatsoever. I went to the pub, I tried to impress a girl, and started to tell the girl about what I learned about black holes during daytime. The girl's, of course, not a physicist, and she stared at me like, oh, that guy, I'm Dutch, has smoked too much marijuana. Right? Too much information is interpreted as incoherence, chaos, blah, blah, blah. At the end of the day, heat. Now, the established wisdom is, and you can sort of demonstrate that in normal some dynamical thing. And the answer is yes. It's actually at the moment you're dealing with these very densely entangled states of matter, you're supposed to get answers to these thermalization questions that cannot be possibly explained in any classical way. The possible outcome is as follows. So actually you can do a unitary laser pulse. It's literally like your ETA setup, making this pure state being going into position of energy eigenstates as initial state. Then you let your system go and you look at optical conductivity. And what do you expect? So in a normal system, let's say this is the optical conductivity before you switch on the laser pulse. It's a bound line, right? And it's the optical conductivity of something that is doing a bit of a true peak. We actually write in here momentum relaxation, and then think about it as here. It's thermalizes gradually, right? So you're supposed to see that this little hole is filling up because temperature is rising. And then this dashed line is what you expect given the amount of energy you have pumped in, you know what it is. And this would be the fully thermalized result because all energy has been converted into heat. This is what you expect. What you get out for a strange metal that you hit with a laser pulse is this. Just before the pulse, you have the initial state result. At the moment that the pulse is over, we switch it off actually with a tiny little theta function. As soon as you can measure, your system is at the final temperature. So when you're dealing with these extremely densely entangled metals, thermalization no longer takes any time. You get completely lost in the overwhelmed by the enormous amount of quantum information in a time that doesn't take any time. And you see that you cannot imagine this classically, you know, when you think about having a normal metal, right, you know, it works, you excite lots and lots of high energy electron hole pairs, right, they all bunch together near the free frequency of your laser pulse, and then you have to wait, they have to collide, and they produce an avalanche of lower and lower and lower energy electron hole pairs, and we wait long enough, it looks like a very direct distribution, but you need a couple of hundred of electric collisions to get there. Right, so it's kind of interesting now. This is not an artifact of ADS-CFT. In two tour de force exercises, it was actually explicitly computed in quantum field theory language by Julius Sonner et al. Explicitly in a large central charge zero density conformal field theory, and by Subir himself in his SYK model. In both cases, you find this instantaneous thermalization. Okay, this should set the mindset. We would love to see this measured directly in condensed matter physics. So I spent a year in Stanford in Zixen's group, among others, and he has a ultra-fast RPES effort running. Bottom line is they are trying it, but it's very hard because basically the time resolution is not of the kind that you really can follow thermalization in any metallic electron system at the moment. But they are at least trying to see whether there's anything of this ultra-rapid equilibration to be seen. Okay, this is basically to set the moods that weird surprise can happen. And now I would like to get back to the Planckian dissipation. Planckian dissipation is more related to a linear response regime, and let's go a bit more interested in that. Let's go to a hydrodynamic regime. Right, so it is the way that normal fluids work, and then you say I have to identify elements of fluids, and they need local equilibrium, right? And then you go a tiny bit out of equilibrium. It's no longer linear response hydrodynamics, and then you get, you know, to see things that you expect to see in water. It should be described by Navier-Stokes, etc. And the basic claim is that the Planckian dissipation densely entangled physics should give rise to a basic flow physics of electricity in things like the cuprates that looks more like a dense fluid like water than this kinetic gas theory. How do we know it? Here, I think ADS-CFT really made a big difference. So you have a system that's very densely entangled. It's not necessarily, you know, associated with any critical point. And then you let a system exist in a Galilean continuum. You have particles that are conserved. You have momentum that's nearly conserved, perhaps. Then the question, how does your fluid looks like at a final temperature? The answer is it should look like a Navier-Stokes hydrodynamical fluid, but it has weird hydrodynamical parameters, especially the parameter that is regulating the dissipation, which is the viscosity. The very early prediction of this ADS-CFT business is actually that the ratio of the shear viscosity divided by the entropy density is set by 1/4 pi times Planck's constant divided by Boltzmann constant. And this is called the minimal viscosity. It's an extremely beautiful and elegant and universal gravitational explanation that I skip. Because actually this minimal viscosity is Planckian dissipation in disguise. And you can see it simply from dimensional analysis. So you sit down and you learn that viscosity can be expressed in terms of free energy density times the moment relaxation time now in a hydrodynamical context where you talk here about finite momentum, more than zero momentum. Your free energy density of a quantum critical system in a CFT is purely entropic, so that's entropy density times temperature, so you know what to do there. Then you plug in the Planckian time, h bar divided by kpt, and you see directly that the ratio of eta over s, is S important, is actually a constant, turns out to be 1/4 pi times Planck constant divided by Boltzmann constant. So it's just revealing that. Now this was a big success because so in no time you get this hydrodynamical fluid. And then these are extremely clever people, and they managed to measure this ratio of shear viscosity to entropy density, finding out extremely close to the holographic prediction against all expectation coming out of perturbative QCD. Right? It happened around 2005, was quite a splash. Now there's a lot more going on. There has been a recent development in the string theory community that has added a lot more excitement to this whole scene. And the bottom line is that you can find very direct relations between microscopic quantum chaos. It's about words like the black hole scrambling in terms of a Lyapunov time and a so-called butterfly velocity, blah, blah. And in these extremely densely entangled systems, you can actually directly relate this microscopic quantum chaos information to macroscopic properties of the fluid, in essence, diffusivity, which is the same thing as viscosity deep inside. You want to read about it, I recommend strongly this very recent paper by Hong Liu and Julian Sonner that is supposed to appear as a review article in Nature Physics. Good. Now I'm getting to the end. I don't think I'm doing too badly. Because I would like to relate this again back to the couplets and the linear resistivity. We actually figured out a holographic ploy for linear resistivity that really works. And it's the only ploy that I'm aware of that really works. This was done in 2004, a little while ago. Back then we had this brilliant postdoc in light literature, Davidson. In the meantime, he is professor in Edinburgh. And for those that has any clue about what ADS-CFT is, we use a strange metal, not the rhizonosum because it sucks, but instead conformal to ADS2 strange metal, which is top-down kosher, turns out to be a consistent truncation, same. They have all kind of beautiful properties. You may know that couplets are supposed to be local quantum critical, Z is infinite. It's marginal firm liquid-like. And it's very susceptible to holographic superconductivity, and it has especially healthy thermodynamics. No constant entropy like Nordstrom, but it has a Sommerfeld thermal entropy. The couplets are known to be Sommerfeld, right? The like in a firmer liquid, that the entropy goes like temperature. Back then we did something which was back then fancy. We used a ploy from cosmology called massive gravity to describe the momentum dissipation. Richard plugged this into the machinery, and what did he find? He find a resistivity as function of temperature being a perfectly straight line starting at the chemical potential, so Fermi energy all the way to zero temperature. Now what's going on here? Turns out you don't have to understand anything of this holography business, because it's extremely general thing. The first thing you have to assume is that you have this very rapid local equilibration. That's the reason I chatted about this probe machinery. Long before the system has discerned that there is disorder that will wreck any attempt to do hydro, it's already equilibrated. It's absolutely untrue in any normal semi-classical particle system like the Fermi liquid or something, right? Because long before two of these gas particles collide against each other, they've met disorder and their single particle momentum has been destroyed. So please do your old-fashioned root theory because it works well. But this stuff is just outrunning that. Then you can establish very rapidly local equilibrium. And then it gets very simple, because when you have local equilibrium, you have hydro. And now you can just rest on 19th century notions from hydrodynamics. First one is resistivity will be typically set by viscous drag, meaning that the momentum relaxation time is set by the diffusivity of the liquid divided by L squared, where L is the distance where the fluid discerns that the stational symmetry is broken. Call it mean free path. Then we can use the relation between diffusivity and viscosity. That's just the mass density sitting here. And then we learn that viscosity is supposed to be minimal viscosity. That is the big assumption out here next to this very rapid equilibration business. So viscosity goes like entropy. In other words, viscosity goes like entropy, diffusivity goes like viscosity, the momentum relaxation rate goes like diffusivity. In other words, resistivity goes like entropy. And it's of course absurd. When you're trained in transport, how can it be that resistivity is just proportional to entropy? For those that are very quick, here we need local quantum criticality, because this order is about length, and length will run in a renormalization, except when you send C to infinite. Then length becomes completely marginal. And therefore there's no extra temperature dependence coming in from the running of the disorder strength. Okay, now this is very beautiful, because we learned in 1992 or something from John Loram and Jeff Talon that the entropy in a strange model of the cuprates is actually Sommerfeld, right? So it's linear in temperature, meaning that since the entropy is linear in temperature, the resistivity has to be linear in temperature. And this is a great universal understanding of why this line is so straight. It's the same reason as that the entropy as function of temperature line is also, or specifically this matter, is also so straight. Now you plug in numbers, and on a number you don't quite know, you actually know all numbers here. It's kind of interesting. The only number you're not quite sure about is this mean free path number. Now you plug in numbers, able to get the prefactor right. You find out that this is something, you know, of order 1 to 10 nanometers. Which is very reasonable, because in order to see the disorder, please make this cuprate electron matter a bit more normal, and that you do by doing your charge order stripy stuff. And we know that the stripy order is typically disordering on a scale of about 1 to 10 nanometers, so it all fits. So far so good. So we wrote this down in 2014, and we didn't pay too much attention to it, you know. But then in 2018, Louis Taillefer et al. Came up with some data showing that this prefactor of the linear resistivity seems to scale with the entropy, and this is what we would expect. They have a different interpretation, which is manifestly nonsensical. I told Louis, but he is not a great theorist, he doesn't seem to grasp it. They would like to prove it, And you can actually prove it. So you take lots and lots of samples. You check whether they have linear resistivity. Then you measure the optical conductivity. You extract the root weight and the root width. And then the hardship comes because you have to measure the specific heat, electronic specific heat in the high temperature sense metal regime to be sure that you grab the right specific heat. And it's very hard to do. And since John Loren died, nobody seems to be capable of doing it. And then you just check whether it is actually consistent with the root width that you measure. And then you establish that entropy and root width hangs together, and you basically assume that this order is not much changing, and that you should try to check as well by looking at stripes, etc., this ordering length. Now, basically, we're waiting impatiently already a little while, but experimentally taking it up. The bad news is the specific heat measurements. So I'm basically trying to pressurize all kinds of experimental groups in taking this up again. Good. I'm nearly there. One more thing to tell you, which would be a very direct confirmation of this type of physics. You may remember that David Price and Bob Laughlin and Phil Anderson were talking about quantum protectorate around 1995. It was based on the observation that you take your best 1, 2, 3 samples, so optimally doped, blah, 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 very clean. And you look at your linear resistivity and you extrapolate it to 0, and you don't see any intercepts, suggesting that there's no such thing as residual resistivity. It's kind of outrageous, because when you do anything, you always have residual resistivity. There's always this order. It should be momentum dissipation at 0 temperature. However, when you believe our minimal viscosity hypothesis, there's no such thing as 0 temperature entropy as far as we can say. And therefore, because entropy goes to 0, viscosity goes to 0, and a perfect fluid having a vanishing viscosity is unstoppable, so it should have 0 resistivity. So we explained it. So I find it actually a very striking thing. Fast forward to 2017, and people at the Florida International High Magnetic Field Lab were looking at the superb Ivan Bosewicz in layer sample 204. 204 is intrinsically very dirty, but they measure the resistivity in the optimally doped sample, and they find out there's no intercept here. Right? So the presence or absence of this intercept is blind for how clean or how dirty your sample is. So it's very striking. If true, you may guess it. We're talking hydro, and hydro is governed by a number called the Reynolds number. And the Reynolds number goes like 1 divided by the viscosity. And the Reynolds number is famous for distinguishing hydrodynamical flow from laminar, for a small Reynolds number, to turbulent. Now you plug in your numbers out here, and you imagine that you make some kind of quantum transport device having, say, constriction, and you find out that it should be extremely easy to get here turbulent flows. Now the bottom line is, and here I gonna basically and you may know about this whole development measuring hydrodynamics in an extremely clean conventional system like graphene at finite density. It's basically pushed forward by Andre Geim, who is a brilliant man. And they make these transport devices, and they have real overwhelming evidence that in an extremely clean conventional system you can get hydrodynamic electron flow. Now the bottom line is that, and I just skip the rest, that Andre has Ivan Bosewicz samples, and they're trying to make these transport devices. There's also a Swedish group doing it, and actually shortly before our Corona friend made lab life impossible, I got an email by Andre claiming that they have some kind of a signal out there that looks like the right way, and I don't want to explain it. It's actually samples all made out of Ivan's in layers. Here's a signal. I don't want to explain it. It's still pretty confusing, blah, blah. And they are busy actually trying to reproduce these signals. When they're there, we will have proof of hydro behavior in dirty cuprates, which is amazing. So when this is true, we have hard evidence for the existence of quantum supreme matter. Okay, guys, my time is over. Oops, a bit more than I planned. When you want to read the story again, I produced a basic tutorial type of a review-like paper that is already published in CyPostFis for a little while. You can find in the archive, and I try to explain this whole story very, very slowly, hoping that everybody gets on board in this really groundbreaking new branch of physics. I hope you enjoyed it. Thank you for your attention.